Before we get started, I want to say that, kudos to the designers of the logo. The most colorful t-shirt. I normally don't wear conference t-shirts for a talk, but I love this shirt so much that I decided to wear it today. And I also came to know that this conference has a tradition of breaking the shoulders of keynote speakers. That is going to be later today. We still have time to take it up. We have one more keynote, isn't it? So let's get started. Well, I want to talk about programming. I love programming. I've been programming for almost 35 years. I program in about 15 different languages. What I'm saying to you in so many words is I'm not good in any one of them. But I love programming and I learn programming constantly. And one of the reasons I learn about programming constantly with different languages is it makes me think very differently. And when I think very differently, I'm able to design very differently. And that helps me to find the solutions that are appropriate for the problem I may have at hand. And in that regard, looking back at time, when I started programming, when I was a little programmer, the systems I was using were, mainframes and VT100 terminals. And you would sit in front of a computer, all you had was a keyboard, and you would type into these monitors, blinking green little cursors, and then that code will get executed somewhere else, who knows where it was. And then as time went on, we had PCs, and we could have machines sitting in front of us. And I'm not even kidding with you. I remember this day very clearly. I went running, screaming on the streets because my machine for the first time had 10 megs of hard drive. And I was absolutely blown away because, my gosh, I am having a 10 megs of a hard drive on my machine. Today, we carry handheld devices with several gigs of memory on it. We have handheld devices with multiple cores on it. And if you really think about it, we've come a very long way. And yet, if you really think about where we are running code today, we're running them on cloud. In faraway machines, we don't even know where they are. In a way, we have come a full cycle. Having gone through all of this, we are back to those systems that run remotely. But definitely things have changed a lot in the world of computers over the past about 50 years. I just turned 50 last year, and as part of turning 50, different people do different crazy things when they turn 50. And I sat there and thought to myself, what do I want to do? How do I want to celebrate my 50 years on this planet? And I came up with the crazy idea. I would never recommend anybody to do this again. And I blogged about it and said, hey, I'm turning 50. I want to speak in 50 user groups and around the world. And within about 2 to 3 weeks, I had most of the user groups signed up. And I spent my year of my 50 years traveling around the world, speaking in 50 user groups. I'm not complaining, but it was really tiring. I felt like I was going to be 100 within a year. And of course, I couldn't complain because the 50th user group was on top of Eiffel Tower, celebrating the Paris Java user group's 10th anniversary as well. So I had a blast doing it. But also gave me an opportunity to think back at the 50 years I've lived and the changes I've seen around me. And it's absolutely phenomenal when you think about it. For example, all the way from those kinds of machines and VT100 terminals to all the way to handheld devices. And we have seen this transition and changes. I remember as a young programmer sitting and playing endlessly in the night with the next computers and absolutely blown away by those kinds of hardware and machines available. And of course, that also brought back something as you grow and become older. One of the really interesting things is to see the next generation grow up. And there was a day when my wife and I were at the store with my son. And my son at the time was maybe about 11 or so. And we were going through the store. And in one shelf, we saw the correction fluid. And my wife jokingly said, oh, wow, look at those correction fluid. We haven't used that in a long time now. And as soon as she said this, my son was very curious, as he always is, and he said, what's that? And my wife immediately said, oh, that's a correction fluid. When you type on the typewriter, make a mistake, you use that to put it on top of it, and then you whiten it out and you type on top of it. My son is curious but extremely patient. He listens to the entire thing, and then he asks the question very quietly, what's a typewriter? And immediately, I should have known better. Instead of being quiet, I immediately jumped on it and said, oh, typewriter is a machine that people used to type on stuff. You insert a paper, you roll it forward, you type on it. And I went on to say, did you know that at one point Dad did not know typing? Your grandma actually typed Daddy's entire thesis. I would tell her what to type, and your grandma is the one who typed the entire thesis. And he listens to this very painfully, and then he says, but why do people do that? Why can't you just use a printer? And that's when I realized I'm talking to a generation which will never understand this. And I immediately ran home before he'd come home and rushed to my closet and started hiding floppy disk I had in there. What if he one day figures out that Daddy once used floppy disk for his work? And then I realized that we are going through this time of transition, and technologies that we once used are in the museum already. And to me, that's just amazing to just live a lifetime and see the emergence of technology, asking what it is, and then asking why anybody would use it, only within a span of a short time. And that's pretty amazing. Now, of course, a lot of things have changed in the past about 50 years. But I'm curious, well, things have changed so much. What do we do with all this technology? And I travel around the world. I'm in several airports. I'm in several offices. I'm in several buildings and cafeterias and restaurants and coffee shops. And I've come to a very grim realization of this. You know, I have friends who would tell me how rooms like this would be filled with computers. And the one thing they were really good at is generating a lot more heat than you could imagine. But today we have on handheld devices much more computing power than those big machines once did. And so what do we do with all of this? And by travel, I've noticed this empirical evidence. And here's my summary of how computers are used today, how devices are used today. I'm going to say I admire the human quest to create powerful devices so fellow humans have options like never before to play the game of solitaire. That's what people are using devices for mostly these days, which is a bit of a shame actually, because we got more computing power today than ever. Are we really putting a good use of it? But then, of course, when you look at the world of the business and the world of the social media, we can quickly see how things are changing very rapidly. And we live very differently today in terms of the applications and the demands on the application than once we did. But the question to ask is, how are we programming in the new century? And if you look at most of the code around, we come to a very grim realization. We program not very differently than once we did. Like I said, I've been programming for about 35 years. And in my younger days, when I was newly married, my wife would, she knew a little bit of programming. She's not in a programming profession, but she knows she lives with a programmer. So she has unfortunately had to see a lot of my bad code. And a few months ago, I was sitting and programming at my desk, and she came in to do something, and then she kind of quietly gleaned over my computer. And then she said, oh, Venkat, I'm so surprised. After all these years, you still are writing C++ code. And then she walked away. I said, no, come on over here. This is not C++. This is Java code. And then she came and said, really? Because it looks like C++ to me. I said, no, not fair. Look at this code. You don't see a single call to delete anywhere else. And that was my defense against the code. And she looked at this and said, okay, I'll give it to you. You don't have any delete, but you have a for loop, you have a if statement. It's pretty much C++ without a delete, and walks away. And unfortunately, she's actually very true, isn't it? So how do we write code in the new century? Well, we do the same old stuff. The for loop and I equal to 0, I less than, and then we write code like this. At some point you wonder, is this the way to the future? Is this the way we want to be writing code in the modern world after 30, 40, 50 years? But of course the question is, why does Java code look so much like C++? Well, that's because why does C++ code look so much like C code? And there's a reason for this. And one of the reasons is programmers, unfortunately, unfortunately, don't change paradigms so easily. It's incredibly hard for us to go do something completely different. We cling on to things and we make changes very incrementally. And that is one of the reasons why we do this, but I'll expand on that a little bit later. So some things are really fundamental and hard to change. And that's going to be the case for a very long time. For example, we talk about programs being Turing complete, which is really great because we want to know that a language can be used to solve general purpose language problems. And Turing completeness gives us an idea that, yes, this language qualifies to use it. Then we talk about the von Newman bottleneck and how the data is moving between the memory and the CPU and how we use the instructions and process them. So those limitations, unfortunately, continue to stay with us. But if you really think about the programming world, let's think about object-oriented programming. Now, does anyone here remember what year OOP was introduced? Any ideas? 1967. So 1967 is when object-oriented programming was actually introduced. It was these two gentlemen, Dahl and Nygaard, two Norwegians, designed one of the very first languages that could be considered object-oriented programming language. They introduced Simula. They quite did not coin the term object-oriented. That term was coined by an American computer scientist, Alan Kay, but the ideas of object-oriented programming came out of these gentlemen's work, and this was back in 1967. Now, of course, today we use object-oriented programming, sometimes even without questioning. We could say OOP is a mainstream. But does anyone remember the year when OOP became such a standard way of doing things? We didn't even question it. We kind of started following the bandwagon. Anybody remembers that year? I'll give you a clue. It was after 1967. No? Yeah, right about the time, end of 1980s to about early 1990. Now think about this for a minute. How many years was that? 23 years. What is 23 years? That is when somebody was born and becomes an adult. That is a long time, isn't it? If OOP was a human, it had a neglected childhood. Nobody wanted to do anything with it until it was 20 years or older and suddenly, hey, do you want to hang out with me? And all of a sudden, people were interested in this. So that was a very long journey for something to become mainstream since the time it was actually introduced. And that was a very slow journey, in my opinion. But what about functional programming? That is the new rage, isn't it? We all talk about functional programming and how we can make our code more functional. Now, when was functional programming introduced? Even better, let's think about when some of the underpinning concepts of functional programming introduced. Like, for example, the concept of lambda calculus. Does anyone remember the year when lambda calculus was introduced? What do you think? Can you try? 75. How about 1929? So everyone here knows of Alan Turing. This was Alan Turing's professor, Alonzo Church, and he introduced back in early 1930s, 1929, 1930s. Now, one last question for you. When did functional programming become mainstream? Okay, that was a trick question. Don't try to answer it. Not yet. A good 90 years later, we are just warming up. We are just getting excited about this. So when people often tell me that things change really fast in our field, I always pause to ask them, what are you smoking? Because it takes 20 years, 30 years, 40 years for paradigm shift to happen and become mainstream. If that's what they call as being fast, I think we have a misunderstanding of the word fast. It takes such a long time for things actually to change. So that brings up the question, why does it take so long for things to change? And if you think about 20 years or 30 years, what is that really? 20 or 30 years is a new generation. And this is something I'm beginning to observe and notice quite a bit. I am about a little past 50, and very soon I'll be approaching my retirement. I am way here in the sunset phase, getting closer towards that, so to speak. But then I turn around and look at very young people, my own children who are becoming adults and entering the workforce. And it makes me wonder, there is a reason why it takes about 20 years or 15 years or even 30 years for things to change. Part of the reason is, don't get me wrong, there are always outliers, there are always exceptions to the rule, but in general, when you look at the world full of people, I think I can notice a pattern. And to understand this, it reminds me of an experience I had. I was in a conference and I gave a keynote, and when I finished my keynote, I got off the stage and I sat down. And next to me was this wonderful lady. She looked at me and said, "Hey, thanks for the keynote. That was a very exciting topic. Thanks for coming and speaking." And I said, "Yeah, thanks for coming here." And she immediately introduced herself and she said she has completed a master's degree and she has been working in the industry for 2 years. Now think about this for a minute. If a lady tells you that she has done a master's degree, finishing the school system, going through a 4 year of college, going through a master's program for a couple of years, and has been working in the industry for a few years, you kind of can estimate very quickly how old she is. And I said, "Well, that's great. I'm really thrilled to hear that you've gone through the journey and you're working in the software field today." And she said, "But can I please ask you a personal question?" I said, "No, lady, thanks for coming. We don't do personal questions, but I'm glad you enjoyed it. We are done." And she said, No, please allow me to ask this one personal question to you. I promised you I'll just only ask you one question. I said, "All right, fine. Just ask me one question and go ahead and ask it." And she said, "Please tell me what year you graduated from college." I said, no, we're not doing this. We're not going to talk about when I graduated from college. She said, no, you promised me you'll answer one personal question. That's my question. You have to answer it. And so I told her what year I graduated. And the minute I said this, her face just blossoms and said, "Really? That's the year I was born." And I was like, I didn't know what to say. I stared at her for a minute and I said, "Would you do me a favor?" And she said, "What is it? Whatever you like, what can I do?" I said, "Can you reach over and get that cane for me? I need some help to walk from here on." And I went back to the hotel that evening and I was thinking about it and I felt totally liberated. And I said to myself, wow, here is somebody who was born after I graduated from school. She was in diapers when I was working in the industry. And here I'm sitting next to her, shoulder to shoulder, so to speak, as a colleague in the industry. And I can talk to somebody about programming and technology. And I said to myself, this is amazing. And the reason this is amazing is looking at these young people, the new generation, looking at my own children, they are naive at times, but they come to you and ask the question, "But why? Why are you doing it this way? Why can't you do it differently?" And they ask that question with a little bit of naivety, but such an optimism, such a courage to say that things can be different. And I realized at that moment something absolutely phenomenal. And they say those who cannot remember the past are condemned to repeat in the future. But yet the people who are young come with such a force to question the authority, to question the status quo, and say that things can be different. And then I realized there's a reason why programmers don't adapt too well. And one of the reasons for that is when we are young, we question, we change, we tell that the world has to be a different place, and then we gain this thing called experience. Unfortunately, the word experience, with it comes this thing called comfort zone. And when we get into this comfort zone, it becomes absolutely comfortable. And I say that when you're young, it's like standing. You have to keep moving when you're standing. You cannot stand still for a long time unless you're the guy in front of the Buckingham Palace who can stand like this forever. But rest of us have to be moving. When you work for a few years, what happens? You tend to sit down. This is a lot more stable, isn't it? And what is 5 years of experience? It is this. Because you are like, oh, this is so comfortable. When somebody says they are 10 years, I don't want to, lay down here, but you get the point. But you are laying down on the sofa with 10 years experience, and somebody comes to you and says, get up. You're like, go away. Don't bother me. I have gained this experience. I am comfortable. I can code in my sleep. Don't tell me this nonsense called paradigm shift. I'm really good at it. In the meantime, these young people who are standing are like, we could do things differently. And you're like, you're tiring me just by talking. Be quiet. And this is the transition we go through. And then I realized, and yet there is something absolutely rewarding. And that is all these people with experience like me, slowly we kind of gain experience, but we fade away. And this new generation with all this energy comes over and says, what can we do differently? Why can't we try new ideas? And then that evening, as I was sitting there, I realized something that was completely liberating for me. And that's when I realized what an amazing thing that nature comes with a built-in automatic garbage collector. This to me is the best thing in the world, is because it takes 20 years for things to change because the garbage collection is rather slow. But as it keeps collecting this and moves us forward, a new generation comes and questions the way they do things. And it's time for that generation to gain that experience. And for the next generation to then come and question them. And then they move us forward. And to me, that's pretty liberating. So we get to really move forward one generation at a time. We take changes in bite size, and it takes time for these kinds of changes to happen over time. And habits are really hard to change, and that's one of the reasons why it takes a generation to change, and we need to have patience for the change to happen. But we are poised for another big set of changes, and that happened, not surprisingly, about 20 years ago. And this actually started emerging between 2003 and 2006. So we are about 15 years into it today, give or take, to approaching the 20-year mark. Now, this is a great time because finally that change is going to push us into the next generation, and we are going to start seeing things, and we are seeing this already. But that kind of change emerged in two fronts. One is imagine the day when the engineer walked up to his boss and he said, hey, I could not put more onto this processor because it's getting so hot that it runs faster, but it begins to melt away. So we started programming, or creating rather, multi-core processors. Today, you cannot buy machines with a single core, and this is the de facto standard. And we are beginning to see machines with literally hundreds and thousands of cores on it. And this changes the way we do multi-threading, and the demands on concurrency goes through the roof with this kind of technology. So on the one hand, the hardware has changed on us already. On the other hand, the business around us has started changing as well. We have very high demands on the business, how we interact with each other, the IoTs, the internet-enabled devices, and the big data, and all the things around us have posed a demand on how we start creating applications, because the business world knows about this and demands using some of those things as well. And in terms of that, we are looking at big data, we are looking at microservices, we are looking at machine learning, AI, cloud computing, and so on. And of course, we see a few emergence of these things in our workforce, things related to, for example, NoSQL, MapReduce algorithms, reactive programming, things that can get us scale and performance as well. We are moving in that direction. But I want you to think about how the programming world is still trying to catch up with all of this. How do we create web applications today? Well, I call this the old web. And the way we do this is, unfortunately, still very old way of doing things. What we created a good 15 to 20 years ago. And that is the stateless request response protocol. So what do we typically do? You make a request to a web service or a web server and you get a response. And when you finish it, what do? You reinitiate a request. And how does this feel when you have to make a request and you get back either a JSON data or HTML data, but nevertheless, you are making a request every single time? Here is a way I would want to describe how this interaction feels like. This interaction of a web development for a programmer like me, it feels like talking to Dory in Finding Nemo. Remember Dory in Finding Nemo? What does Dory do? Hey, I'm Dory. How you doing? And only a few seconds later, hey, I'm Dory. How are you doing? And every few minutes, you have to reestablish your context. That is how I feel when I code these systems. I feel like I'm working with Dory over and over, right? So that's not the way you want to interact. Imagine this for a minute. Imagine I see you at 6 p.m. yesterday. You were going out of the door, and I ask you where you're going, and you tell me you're going to watch this movie. And maybe I see you at breakfast this morning, and I ask you, hey, did you go to that movie yesterday? And you said, yes, I did. And then I ask you, how was it? And your response is, how was what? That's not the way we humans communicate, isn't it? We can have a conversation. Hey, did you go to the movie? Yes, I did. How was it? Oh, it was great. Really? And I can continue with the conversation with you because we maintain a conversational state. What if we can maintain such a conversational state in our programming? And I want to envision this as the new web. And we're not really far from this. And this is where we are seeing the emergence of things like continuations. Let's take a look at an example of this really quickly. I'm going to show you an example here in JavaScript. I know that's a bit scary for some people, but I believe in learning from almost everything we can get our hands on. So let's take a look at how this would feel if we can have continuations. We know there are two things. One is called a subroutine, and a subroutine is just a function. You make a call, you get a response. You make a call, you get a response. And subroutines do not carry any state with them. On the other hand, we can go to what is called a coroutine. And a coroutine, on the other hand, is, if I know how to type this morning, so a coroutine, on the other hand, carries a conversational state. So you can call a coroutine, but a coroutine has multiple entry points. You enter at the top, but then you don't leave at the bottom. You can leave in the middle, but you can come right back where you left and you can continue the conversation. Like I say, how was a movie yesterday? It was great. Did you like it? Who was the main actor? I can continue with that conversation moving forward in that function as a conversation. So how would this feel like if we were to write code like this? So let's say we create a function. I'll call it foo for now, but I'm going to then say here for, let's say, constant element of, let's say, foo for a minute. Then I'm going to simply display in the loop, let's say, call here in the loop, but then I'm going to display that value of the element E within the loop. Now, of course, this code won't work as it is right now, but I'm going to turn this into a generator. And then I'm going to simply display here something like, I'll just simply say entering the function. So I'm going to say entering the function, and you can see that it says entering the function. But at this point, I'm going to simply say yield, and I'm going to yield a 1. Then I'm going to run the code. It says in the loop 1. But at this point, what I'm going to do is simply display over here, let's say step 2, and I'm going to yield 2, but then I'm going to say over here, let's say step 3, and I'm going to yield a 3. But now this time around, when I run the code, we're not leaving the function to entirely come back into it. So in a way, what we did here is we entered this code right in here, but we exited it right here. But then we came right back into here. Now, looking at this code, you may say, wow, what's going on here really? Now, I want you to think about two different concepts in programming and then connect them together. One concept I want you to think about is this idea of a tuple. I love tuples. Tuples basically are a data structure that can contain typically a pair of data, but potentially any number of arbitrary data, and often they are immutable. The other thing I want you to think about is a closure. Now, what is a closure? A closure is really a lambda expression, but with one difference, lambda expression with immutable state. That's what closure really is. So a closure is a lambda expression with immutable state. So in other words, it's an anonymous function that can carry a state around. Now, with these two ideas in your mind, look at the code we just saw here in front of us. What if this code is returning a tuple? And where the tuple it is returning is going to start right there, with the 1 being the first value of the tuple, and the highlighted code becomes a closure that becomes part of the tuple. So this tuple is returning a value which is 1 and a closure which captures the rest of the code. Now you can come back and call that closure, and when you call that closure, it can start running on line number 8. But line number 8, when it executes, in return, it can send back another tuple which contains 2 as a result and the remaining code as a closure. Now, this idea of taking this and capturing this over has a name for it. It's a data structure called continuations. And continuations have been around for a very long time, 40 to 50 years. The point I made earlier, new old things are new again. And all of a sudden, we are getting excited about continuations. I'm going to make a bet here today. In the next 5 years in Java, we will not be doing as much multi-threading as much as we'll be programming asynchrony. If you want me to bet my money on something, I am betting my money on something emerging in Java, which is called Project Loom. And I'm absolutely excited about Project Loom because Project Loom contains 2 things. It is made of continuations plus fibers. Let's take a quick look at how that looks like. So here is Java code. This is Java code running on Project Loom. This is not available in binary form yet, but you can compile, download, and compile it on your machine if you want to. But I'm going to say over here, simply starting out, I say val, or rather var, and I'm going to say scope is equal to new continuation scope, and I've created a scope object. This is in Java right here. Then I'm going to say over here, continuation is equal to new continuation. And to this continuation, I'm going to provide the scope, and I'm going to provide a little lambda expression. We will call this one here as do work, for lack of better words. And that's all I've done so far is I've called a function called do work. This function do work is going to take a continuation scope as a parameter. And let's get started with this part. And what am I going to do right here? I'm going to say entering function. Just like in JavaScript, I'm writing this code here in Java. But then what I'm going to do here is, as a next step, I'm going to say while continuation is not done, I want to say continuation.run, but I'm going to then display right here in the loop, and I'm going to simply say those words here in the loop and just run it like that. So what does this do at this point? So I have a do work method, and of course I'm going to use a continuation scope that's got to come from somewhere. Import java.lang.continuation .star, and I'm going to bring in a static import into it. We'll come back to using a yield in just a few minutes. So this is going to be the do work method that takes a continuation scope, and And I'm going to use that effectively at some point. Let's see what the error tells us right here. So it says the method do work of the class cannot. Continuation scope requires an argument. Of course, my fault. I should be passing the scope right in here. So let's go ahead and try that little code out. So you can see that it says in the loop entering the function, but then I go back to this code and I'm going to say in this case yield, and I'm going to yield and I'm going to pass the scope to that yield where the yield is coming from the static import. But then I'm going to simply say step 2 as we did earlier, and I'm going to yield one more time. And then before we finish this up, let's do one more time. Output, let's say in this case, step 3. And of course, at the very last step here, I'm going to go ahead and simply call a yield one more time on this one. So when I run this code here, you can see the Java code doing something very similar to what the JavaScript code did. But of course, you wouldn't be using continuations like this when you write code. Fibers are lightweight threads, but Java is going to have the ability to do non-blocking calls moving forward when Project Loom becomes available for us to use. And within the next 3 to 5 years, we'll be writing asynchronous code in Java, much like we do in JavaScript. And all of a sudden, we can start thinking about creating web applications where a conversational state can be maintained. And imagine creating a workflow through a web service where you don't have to be doing that like the way we do today, but have a conversational state built in, and we can have messages being exchanged and conversations carrying the context using closures. That's going to change the way we can think about how we would program these systems moving forward. So this gives you an idea about where we are headed in terms of continuations, and we can start encouraging some of these ideas. But like I said, these ideas have been around for a long time, and yet most of us have not used it. This is one thing I will emphasize. I remember as a very young programmer reading about these things in books and magazines and articles, and I would stare through the window and say, oh my gosh, how cool would it be to actually do this? I'm reading something in theory, but I'm not able to use it. Why? Because the mainstream languages that I was using did not have these features. And sitting back 30 years later, I am absolutely blown away because the concepts I've read about as a child are now becoming part of the mainstream languages. And you can use them readily. And to me, this is very empowering because we don't have new technologies, we have new availability. And what I mean by this is truly the democratization of technology. What I could only read about when I was a child, what I could only imagine as a child, unless I worked as part of an elite organization or I was part of a unique research group, I only could imagine otherwise. My children can access these things for just a few cents a day. And to me, this is democratization of technology. And when people ask me what I think about the world is, my opinion is the technology and the availability today has reset the playing field. It doesn't matter today where in the world you are, which country you're living in, where you went to school, it doesn't matter. As long as you have that passion, as long as you have that curiosity, you have technology within the reach only for a few cents or less. And that to me is very empowering. And so these ideas are emerging into the mainstream so we can start using them. So continuations give us the ability to save the execution state and return to that point later in time for execution. So what do I expect in programming languages? In continuing this particular approach of making these ideas available in mainstream languages, there's a convergence of languages moving forward. And languages should make simple things simpler and harder things manageable. And I want to really not invest huge amount of time and effort in implementing ideas. It should be very approachable. And languages must promote a higher level of abstraction. So what are the things I want in languages? I want them to promote higher level of abstraction. I want languages to promote composability, and I want languages to be more declarative in style. So to outline some of these ideas, the first thing I want languages to do is be very expressive. Let's talk about expressiveness of languages just a little bit. So here's an example, if you will. I'm going to say names is equal to, let's go ahead and say Jack, Jill are the two names. Now I want to iterate over these and display the values. How do I iterate and display the values? You could start by saying name. Well, in this case, you could say I equal to 0, I less than names dot, and then you ask the question, is it size? Is it length? Is it count? There is not enough time in the day to decide it, isn't it? And once you think you found out, what is the next thing you do right after that? You ask the question, is it less than or equal to? Do you ever ask this question? Every single time. When people ask me, what is the symbol? I tell them that is the international symbol for I feel stupid. Because every time you type it, you got to ask the question, what is it? Less than or equal to? This is such a waste of time, isn't it? Very low level abstraction, too many moving parts in it. Well, what can we do instead? What if we were to say over here, name of names, and simply print out the name given to us in one shot? Hey, that's very easy. But what if I really want to print the index and also the element? Oh yeah, that's why the old loop was really good, because we use the index. But that was painful though. What if we can do the following? What if we can print out the value of the index I, and then what we can easily print out the name as well? But where in the world the index is coming from? Well, we can now go back to this and say entries. And as we get the entry, every single entry, we can use a beautiful concept of destructuring, and we can get the ideas through very effectively. So this becomes an idea of destructuring, where the code becomes really expressive, where as you're iterating through every entry in this array, you are destructuring the values. Structuring is where you're creating an object. Destructuring is the opposite. You pull the properties out of an object. What if the code can become intuitive like this? Here is another example of this here in Kotlin. So I'm going to say over here, fruits is equal to, I'll create a mutable list of, let's say, apple, comma, let's say orange. So I've got a list of apple and orange, and I want to print out the fruits we have with us. So you can see in this case, we have a collection of fruits I'm going to use. I'm going to actually say list of, just create a immutable list that's good enough for our purpose, and right there is orange and apple. But what I want to do at this point is I want to add one more fruit to this. What did I say just now? I said I want to add one more fruit to this. Well, you could try that way, and you could say add maybe a banana. But why? I know what the word add is. I learned that back in elementary school. And what do I do for adding most of the time? I simply say plus. Why can't we just write code intuitively by making the code really expressive, so we don't have to really work that hard? When the code becomes intuitive and expressive, it removes the impedance for us, and we are able to write code very effectively, very quickly. So the point really is, if the code is expressive, we are able to focus on getting our work done rather than getting dragged by the ceremony of languages. I want composability as well. This is one thing Java has done fairly well in terms of Java 8. Now, we all know about composability in the case of Java. Let's think about this for a minute. If I have a string of names is equal to, let's say, list of, and I'm going to put some names here, some names, and all I want to do is to print all the names in uppercase of length 4, I can simply say names.stream. Then I can say filter given a name dot-length is equal to, I can simply say a length of 4. I can perform a mapping of a string to uppercase, and finally I can say here for each system.out, and we can simply print it with a print line over here. So this composes really nicely, as you can see, where we can just flow through and apply transformations to get the work done. When the code becomes composable, it becomes a lot easier to work with. But composability doesn't simply mean you can use the Streams API. I'll give you one other example of a beautiful composability here. So I'm going to go ahead and create right here in Java 8, I'm going to ask for, let's go ahead and say, I'm going to bring up a function. So this is function integer comma integer, and I'm going to say increment is equal to given an element plus 1. So what I can do here is I can increment and I can call apply on it and pass a value of 5, let's say, and 5 plus 1 is 6. And that's very easy to do. But on the other hand, if I were to create a function, we will simply call this function as, let's say, use, and I'm going to send a function of integer, and I'm going to call it func. And all I'm going to do is simply output right here, func.apply, and a value of 5. And I'm going to call that function from here. So all I'm going to do is pass use the increment function. And of course, 5 plus 1 is 6, and it prints out the value of 6, as you can see. But what if I were to create one more function, and this function is going to be double it, where it's going to take the element given and it doubles it. Well, at this point, of course, I can call use and pass double it. 5 times 2 is 10. So 6 and 10 are the result. But what I really want to do here is I want to increment it and then double it. Oh, darn it. How do I increment something and double it? Well, here's an idea. We could create a function integer comma integer, inc and double. And then, of course, e is equal to, and then e plus 1. And then we could try to do it times 2. But that is so sad, isn't it? Because that's not composing anything. That will not invite friends if we do that. So what do we do instead? We can simply say increment and then double it, and we can compose functions together and be able to combine these operations. Composability is a very important characteristic in programming. And we often do object composition in OOP. But in functional programming, we need to be able to do functional composition. And the ability to compose functions becomes a very important thing to do. And languages are moving in this direction quite a bit, as we can see over the years, and that's in the step in the right direction. You want the code to become really efficient as well. So from that point of view, going back to this code right in here, we have efficiency, all right. But the question really is, this code here, how efficient is it? What if I'm interested in not printing all the values, but I'm interested in the first value? I'm going to say find first. And once I find the first one, what do I want to do? I want to simply say for each and print it, system.out and print it. I'm going to simply say println. So when I run this code, it printed only Dory, because Dory is the first element which is of length 4. But what if I don't have a small group of values? What if I had a very large collection in front of me? Oh, darn it, that would be really inefficient by processing all the values over and over and over. Well, unfortunately, though, that will not bring friends to us either. You can look at this code and say, you know what, this code is going to process the elements in this collection, but look how beautiful this code really is. And that's what people normally tell you, right? Look how beautiful this is. It's expressive. It's composed. You can read it easily. And if you are like anybody else, you would listen to them and say, but what about performance? And performance is very important to us. And I'm gonna say a theory that I have. This is about 2 things. And I'm gonna say both in life and programming, cuteness is not sustainable. And this is a sad story, but this is true. Cuteness is not sustainable. I always tell my wife this. You know, one of our friends would call us and say, we have a new baby. And my wife will be eager to go see babies. She loves babies. And when we go to see the baby, I'm the one who gets slapped all the time, because she would look at the baby and say, how cute. And I will go to the baby and say, sorry, baby, that doesn't last. Because cuteness in human life lasts for 2 years. At the end of 2 years, what do we tell the children? You talk too much, be quiet. This is humans become annoying as they become older. So cuteness doesn't last too long. And the same thing applies to code. Code is cute, but you're not going to live with the cute code. What about performance? If you don't deliver, there is no point in really looking at the cuteness. So what is the answer to that question? So functional programming is really cute, but it's not enough. So it's expressive. That's what the cuteness comes in, but expressive, all right. But what it really is functional programming is equal to functional composition plus, and a very important characteristics, lazy evaluation. And those two are absolutely important. So functional composition makes the code expressive. Plus, it's efficient, and the efficiency comes from lazy evaluation. The case in point, let's go back to this code, and right here, let's go ahead and call a function called sample check. So I'm going to go ahead and write the function right in here. So this function public, let's say static Boolean, we'll call it check, which takes a string, and we will call this as name. And within here, I'm going to simply return name.length is equal to, let's say, a value of 4. When I run the code, you can see it says Dory. However, if I were to print out here called for, and I'm going to simply print the name, and just to make this a little bit more fun, let's go ahead and say we have in this list Venkat, who is not 4 letters long. When I run the code, notice the output. It called for Venkat, called for Dory. It doesn't call for anything after that. And the reason for that is laziness. So efficiency is extremely important. If Java had given us functional syntax, but it did not give us the laziness of evaluation, you and I wouldn't be talking about functional programming today in the context of Java. So the developers of Java were very well aware of this. So they took the time to introduce laziness into it. But the way they did that is through the Stream API, which leads us to one other important thing. I want the features in the language to be almost seamless, especially asynchrony, almost seamless. And the word almost is very important to me. Let me emphasize this. When Java 8 was introduced, I wrote the very first book on Java 8. I started writing the book 2 years before Java 8 was released. And I remember clearly in the early days of Java 8, way before it was released, the functions like filter and map were part of list and set. These functions were on list and were on set. And one morning, I wake up, download the source code and the unit test from their repository, and recompile the code I have been writing in the book. And to my shock, none of the code would compile anymore. And I'm like, my gosh, where did the filter go? Where did the map go? And that's when I learned they had introduced a new concept of streams. And I was wondering, what is the purpose of a stream? Why can't you leave these methods on a list or a set? And it dawned on me, this was brilliant. And the reason it's brilliant is there's a big difference between functions we already know on a list to the new functions like filter map, which are still different from functions like find first. And that is, these functions like filter and map are intermediate operations. They don't run. They are lazily evaluated. They don't run until a terminal method is evaluated. Now imagine they provided these methods like filter and map on list. The world will go crazy because you look at the list now and say, oh my goodness, are these functions eager or are they lazy? There is no real easy way to tell. So what they did was they introduced a stream, and now it's very clear. Syntactically, it looks the same, but semantically, it gives you a visual cue to say, aha, this is entering the territory of a semantical difference in evaluation. Some functions may be eager, some may be lazy. If a function returns a stream, it is lazily evaluated. If a function returns a non-stream, it is eagerly evaluated. So that becomes easy for us to read the code and get that visual cue. Here is another example I want to show you about this. And that is, here is the Kotlin code I want to show you again. And in Kotlin, I want to create a bunch of functions. So I'm going to call a task1 right here. I'm going to call a task2 right here. And I'm going to simply print out made the calls. And that's all I'm going to say, made the calls right in there. But what is task1? What is task2? Kotlin is a beautiful language, but the creators of Kotlin want you to not just write code. They want you to feel good when you write code. So that's why they called it fun. They want you to have fun when you write code. So task1 is a function. And I'm going to put over here a print line will say entering task1. And similarly, we will print out in here exiting task1. So you can see in this case, we have a task1 defined to enter and exit. And I have a task2 defined here. And I'm entering and exiting a task2 as well. So when I run this code, should be no surprise over here. We have entered task1 and task2. And we have also made the call to those functions. So that's pretty darn easy to see. Great. Now what I want to do is I want to modify this to run blocking. This is to turn this into a coroutine. We talked about continuations a few minutes ago. So import, I'm going to say Kotlin x coroutines dot star. And I'm going to run this as a run blocking. Didn't make any difference yet. It enters task1, finishes it, enters task2, finishes it, and says made the calls. But I'm going to turn this into a concurrent run by calling a launch. And by using a launch over here, I am going to ask these two functions to be fired away in a non-blocking manner. All of a sudden, made the call comes first. Then we enter task1 and completed, enter task2 and completed. But then I can also say yield to not have to block. And I can release the thread so it can go off and do other things. Now, when I say yield, that's a semantical difference in the code. You are suddenly saying, when you enter this function, you may not finish the function. Your thread may go off and do other things, and then you may come back and continue with it. That's a huge semantical difference. Syntactically, it looks very similar to what we had before. Semantically, it's very different. And they wanted us to know that we are crossing a semantic boundary, so we are not surprised about it. For that reason, they made it almost seamless. Well, that's the good news. But the bad news is, I do have an official complaint to make. As much as I love Kotlin, I wish they had paid attention to the keyword they chose. This is very sad. Because to tell that a function has a different semantics, use this keyword called suspend. But who wants to suspend fun anyway? That is so grim, isn't it? I wish they had chosen a different word for it. But now that you marked it with a semantical boundary, when you run the code, you can notice the difference. You made the call, but notice you entered task1, but you haven't finished it. Now you entered task2. And now then you exit task1 and then you exit task2. So in this case, it truly becomes a non-blocking call and you're able to switch between these calls very effectively. So how can we prepare for the future that is ahead of us? We see all this convergence of these ideas. We have seen ideas from 20 years ago, 30 years ago, 40 years ago becoming mainstream. But they're not becoming mainstream all in one day. Languages are pushing each other, motivating them and teasing them to say, look what we can do. What about you? And those languages are beginning to move in that direction for just surviving and also to be able to effectively provide this. So how can I become an effective Java in the future? How can I become an effective C# programmer in the future or JavaScript programmer or name any language? And I think their answer is actually pretty simple. And to answer this question, I'll give you one story. This was a story reported in NPR, the National Public Radio, a research study done by folks in Chicago. And what they did is they brought very small children. And these are innocent children. And they brought two groups of children. One group of children were exposed to only one language. Their parents spoke a language, children in their school spoke the same language, children in their other communities, sports groups spoke the same, play groups spoke the same language. They were exposed to one language. The second group of children, their parents still spoke the same language, but their nanny spoke a different language, or children in school spoke a different language. Even though these children didn't speak multiple languages, they were exposed to multiple languages every single day. They took these two groups of children, and what the researcher did is they had objects in the room. For example, they had an apple right behind, and they had apple behind the person asking the question, and they had apples in front as well, between the children and the person asking the question. And to the group of children who spoke the only one language, they would ask the question, how many apples do you see? And the child would answer 3, for example, where there were 2 apples in the front and 1 in the back. And the child was able to see 3 apples, and the child would say 3. But consistently, they would ask the same question to the children who were exposed to multiple languages, and they would say, how many apples do you see? And these children would look around the room and they would answer 2 and not 3. And the researchers were surprised about it. How is it that children consistently say 2? Because what these children were doing is, when the question was, how many apples you see? These children immediately looked around the room and said to themselves, well, the person asking the question obviously cannot see the apple behind them. So they filter it out and answer 2 because that was the shared object in their common vision. And so they're concluding that when you are exposed to multiple natural languages, you develop empathy. You develop a thought process towards other people, and you begin to think in their mind when you're trying to analyze things. Which is a good thing in general, isn't it? I'm no natural language expert, but I can vouch for you, having programmed in 15 different languages. My thought process is very different today, having programmed in multiple languages, than when I programmed in only one language. So one way to get to the future, in my opinion, is really to reduce the time of learning. Is the amount of time we need to learn a new concept is inversely proportional to the number of diverse ideas that we are being exposed to. So the more diverse set of languages we program in, it reduces the time we're going to take to learn a particular language. And learning different languages is a way to really make the difference. So learn different languages, not all of them to use all of them, but to go back and program in the language you program very differently. So don't wait for the future. It's already here. So one way we can be ready for the future is by diversifying the language portfolio. And the more languages we get exposed to, the easier it is for us to be ready for the future, because the future has already arrived. Thank you, and I hope it was useful. Enjoy the rest of the conference. Thank you.